Okay, hello, folks. Welcome back. Welcome back. Okay. Oh, and my board just stopped again, of course. But okay. Good to see you all. Hold on. Sorry. The board is. This never did used to happen. Well, no, it did happen last semester. It didn't happen as much. Hang on a second.
Yeah.
Hold on. Okay. 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 So first of all, I just want to quickly, and I know time is, this course will accelerate, believe me, but I am watching the clock, but I do want to know first and foremost, can you electronically raise your hand if you were in a room that had any mixture at all, i.e. either a mixture of people that started the homework and people who had not, or a mixture of people who were aware of the 5-step method and people who were not? Can you just raise your electronic hand if there was any mixture in your room? Thank you, Katya. Thank you, Caroline. Thank you, Amanda. Thank you, Caitlin. Thank you, Amy. Thank you, Adon. Thank you, Savannah. Thank you, Mackenzie. Welcome, Mackenzie. Thank you, Irini. I hope tell me if I'm not pronouncing your name right, and welcome. Thank you, Jose. Keep them up, though. Keep them up for a second. I'm sorry, if you don't mind. Thank you, Evan. Thank you, Mackenzie. Thank you, Irini. And keep them up because I just want to see. Okay, so that's a lot. Thank you. But now a lot of people are not raising their hands. So I just want to make this clear to myself. Put your hands down now, please. Thank you. Thank you. You could all put, great. Now, it's obvious, but it's not obvious. Can you please raise your hand if your room was fully homogeneous, like everybody had already started homework or not, and everybody knew the 5-step method or not? Can you raise your hand if your room was all one type, unmixed? See, because now if no one raises their hand, that's a little disturbing. Because a lot of you didn't raise your hand on the last question. This question is the, okay. Oh, Kevin, thank you. Thank you, Sumaya. Right, this is almost the trick question because you got to raise your hand for one of these two. Thank you, Emily. There's still some. So you, okay. Oh, thank you, Stephen. Okay, wait, I'm still going to wait for a second. I mean, this is kind of I got to open a portal for this. Wait, keep them up. All right, wait. Put your hands down for a second right now. All right, thank you. And thank you, Sumaya. And you can put your hand down, Sumaya. Thank you. But you can put your hand down now. Oh, and Rashma, thank you, Rashma. I didn't see that. Thank you. That's helpful. So wait, so Sumaya, put your hand down for a second if you don't mind. Okay, thank you. Okay, wait, I'm going to do the obnoxious thing now. Yeah, I know this is boring and it is obnoxious, but we're still getting to know each other. So hang on. Since those two questions I just asked were the opposite of each other, they were like the only two possibilities, and most people raised their hand, but not everybody. So just to do the control on this experiment, at the risk of being rude, can I just ask you right now, if you hear me at all, if you are paying attention at all, can you please raise your electronic hand? And keep it up, and keep it up. Thank you. Thank you. And keep it up. I mean, this is the obnoxious, but this is as obnoxious as I get, I think, or at least as obnoxious as I get deliberately. Please raise your hand if you hear me at all right now. If you're with me at all. If you hear anything going on, just keep your hand up for a minute, please. This is the test of life. Wait, please. Okay, so some people are not raising their hand right now. I am not. Oh, and you're saying, oh, and thank you. I see some of you are in the chat. Okay, thank you, Rashwan. That totally counts. That's totally legit. So there's like one person who's not. I'm not going to name anybody, even though it's good. Euban, are you with us? Okay, well, all right. I'm not going to go. All right, you can put your hands down now. Okay, so I want to quickly. So let's stay together always, please. So quick question, those people, I do want to hear now substantively for a minute, and I'm not trying to put anybody in the spot, but those people who were in a room that was all one type, right? Like 4 of you raised your hand or so and put in the chat to say that you were in, oh, and Douglas, thank you, Douglas. Okay. Those of you who are all in one type, can one of you volunteer either in the chat or with your voice or something? Tell me if you were in that room where everybody was like of the same genre, can you tell me what that genre was? Somebody like was it all that you had all done the homework with? And even if it's that you all had not done the homework, it's fine. Don't be embarrassed. Like you're not going to be punished. I just want to know where we're at so I know how to teach. So could someone tell me in the room where you said it was all, oh, Douglas, sorry, is that your hand? Douglas, you were in one of those rooms where, oh, no, wait, Douglas, you joined, right. You're raising.
Yeah, I still had it up from before.
Right. Okay. Sorry. My bad. Right. I get it. Because you came in later. Right. Okay. But thank you for your honesty. And that totally counts as class participation, what you just said. In fact, it counts as closing a conversational loop if you want to put in for that part. But so someone who was in that room where everything was the same, I think Stephen was, I think Rashman was, I think maybe Erini wasn't, I'm not sure. Could you, Emily was? Okay. Could you, Emily, awesome. Can you just take a moment either in chat or with your voice or something? Just tell us like what happened in that room. Like who?
I joined a little late, so everybody was also as well finished with their work.
Oh, okay. So they had all right, and all it seemed like everybody in that room had at least started. I'm not trying to. You don't have to name names or anything, but it is your impression was everybody in that room had done something with homework 1B. Is that your impression?
Yes.
Okay, cool. And is your impression, and I know you know from last semester, but was your impression that everybody in that room knew something about the 5-step problem solving method?
Yes.
Awesome. All right, totally helpful. Great. Just what I needed to know. Cool. Okay. So, and at some point I'm going to open a portal for that too. But so we've got like 23 minutes. We're going to start getting rolling now on the sheet. Like I'm going to start going over the sheet. You'll see if your answers are correct or not or whatever. I am expecting when you're handing it in that you're handing it in with the 5-step method. So here we go. Oh, and I will tell you, like the two main equations that will be used for like at least the first 3 problems on the sheet, 3 or 4, are these 2 equations on the board right here. Just as a quick refresher or reminder or review, the second equation on the board right here, F net equals ma, or the sum of all the forces equals mass times acceleration. That's Newton's second law, right? And it has arrows over the F and the A to make it clear that it's a vector equation, that it applies to one dimension of space at a time. So put another way, that equation is really there's 3 axes of space. So that equation really is a package of 3 equations that are independently yet simultaneously true, right? What that equation, Newton's second law says, and it's there because it's like always true in physics. Like it's one thing that I am assuming that everybody who took physics 1 has some exposure to, some familiarity with, some practice with. Like I am assuming that everybody has some grounding in F net equals ma. And I want to remind you that's a law that is, and it's always true and always important and always kind of a beginning statement in almost everything we do in physics, like for the rest of our lives. But that statement is about the general nature of forces, how they act in general. That in general, if you have some mass and you add up all of the different forces that are acting on that mass along some given axis of space, say the x-axis, and then you add up all of those forces, taking into account minus signs, like all the forces pushing in one direction minus all the forces pushing in the opposite direction along that axis of space. If you add up all those forces measured in newtons and you divide by mass measured in kilograms, you will get the acceleration of that object along that axis of space, right? So all the forces acting on a mass at a given point in time and space will yield the acceleration, the instantaneous acceleration of that mass at a given point in time and space along a particular axis, right? So it's true along the x-axis, it's independently yet simultaneously true along the y-axis and also along the z-axis. That statement in parentheses, the bottom statement on the sheet right now, that's true in general about forces, right? And I am, again, sort of assuming people are sort of comfortable or practice with that. But then the statement above it, which you maybe be a little bit less familiar with, is Hooke's law for the character that tells us the expression of the mathematical content of a particular force, the force exerted in particular by one end of a well-behaved spring. The force exerted by the edge of a spring onto whatever mass is attached to that edge. So these are both statements about F, about forces, but the one on the bottom is the general statement about all forces, what they do when they add up together. The statement on the top is the nature of the particular force exerted by a spring on some mass. That's the equation that we're going to be using, at least at the beginning of this homework assignment. And it's called Hooke's law. And so here we go to the assignment. So let's say we're turning in this assignment, right? And I'm walking through what I would be looking for in this assignment. First, I do a kind of quick gross. First, I did step one. Oh, and let me remind also the people that are new. So I'm assuming that you got this assignment, this problem set. It's on the PDF from me, whatever. You take out a separate sheet of blank paper, right? Or a separate document on your computer, and you start solving the problem on separate sheets as though you were writing in the blue books of some exam, like, right? In other words, not on the sheet itself, but you take out separate sheets. And step one, I guess I should have labeled it. This is, well, yeah, no, this is all one problem. Step one, DFP, is diagram and fact pattern, right? So I'm doing step one. I put the diagram down, even though the original sheet happened to have had a diagram. A lot of sheets don't. Even if my diagram looks a lot like it, I've made my own diagram here. I've got a spring with the left end affixed to a wall, the right end affixed to a mass. Wherever the mass is sitting stably at the edge of that spring, wherever it would just sit and stay if I didn't push it or pull it, we call that the equilibrium position. We designate that as X equals 0. X triple equal sign, X is defined to be 0 wherever the mass is stable and comfortable. The stiffness of the spring, the strength of the spring, is identified by this constant number called K. Any given spring, any well-behaved spring that you ever have, has a certain stiffness or certain strength known as K, and it's constant for that spring. It may change from one spring to the next, but for a given spring, the spring is identified by how strong or stiff it is, and that number is called K, and it's measured in newtons per meter, the amount of force that that spring will exert for every meter of displacement to which you subject the spring. So this spring has a constant stiffness of K. It has a mass on the edge of it labeled M. The mass is sitting at the equilibrium position known as X0. And then, according to the diagram, we pull out the spring, we pull out the mass and hold it. We hold the mass at a certain position that is displaced away from equilibrium, displaced, in this case, to the right of equilibrium. So it's initially being held there, wherever the mass is initially being held, like has, oh, I think there's a question. Let me, I'll say this sentence and then I'll get the question. Wherever the mass is initially sitting without velocity, we call X naught, like not X equals 0, X sub 0. And that's called the initial position of the spring. In this particular case, the initial position of the spring happens to be 15 centimeters, 0.15 meters. The mass in this case happens to be 0.3 kilograms, and the stiffness of the spring happens to be K. So everything I've put here, and then I'm going to get Doug. I think he has a question, which is great, and I definitely want the question. I'll just say this. So what I put here is a diagram with everything with everything labeled in it, and I'm calling that step 1 diagram and fact pattern. It's the setup of the problem. It's what I think is the first step that I should do in a 5-step problem solving method to solve any problem I ever get, homework or exam. But that's my setup, step 1 DFP, diagram and fact pattern. Okay, sorry, Douglas, you have a question.
Yeah, so in that diagram, you want all the forces being shown, correct?
So in that diagram, I want what? All the
Forces that are acting on the object, or like normal force, like I don't know if to do that. I know I was taught to do that, but I don't know if you do that part of the method.
Very good question. Okay. Very good question. Let me back up on that. Definitely whenever I'm making a free body diagram, or especially if a problem asks for a free body diagram, which is another way of saying force diagram, then yes, in a free diagram, I definitely want to label all the forces acting on an object. And you're right, in this case, that would include not just the spring force, but it would probably include like mg pointing down, and maybe if there is a normal, if this is on a table, if it's on a table, maybe a normal force of the table pushing up. But so in general, I totally agree with you, and that's a really good habit. Here's the thing. Number one, a free body diagram is a method of solving a problem, which is really important, and we do a lot, but that's once you're already solving the problem. Right here, in step 1, what I'm just asking for is just a picture. Maybe I shouldn't even call it a diagram. I'm just talking about a picture here that presents all the facts, the given facts of the situation, like much like the picture was on the homework sheet. So this, whenever I do step 1 of the 5-step problem solving method, I call that diagram and fact pattern. I just mean a diagram that gives all the information that was given. So things like the normal force or gravity, if they're involved, that's things I have to figure out. I'm not sure if I know them yet. They haven't actually been presented as facts in this. And to be a little bit more specific, I don't actually know that this spring is on a table. This spring could be attached to a wall and coming out of a wall horizontally. Like that would be a legitimate way to use a spring. And then I've got this mass dangling on the end of it. So I'm looking at its horizontal motion back and forth. I'm not saying it has to be that way, but it could be that way. So I don't actually know for a fact. I don't have a factual given that says that this mass is actually on a table with a normal force pushing up on it. All I know is that there's a spring on it. And frankly, all I'm really going to be asked to analyze is the horizontal motion due to that spring. So long way of saying, I think it's a great question. I love free body diagrams. I'm a big believer in them. And yet often they'll involve an arrow for the normal force. But I don't think here, I'm not specifically yet asking for a free body diagram. I'm just saying present the facts of the problem. Does that make, it's a great question though. Does that make any sense, what I'm saying?
Also, I have one more question.
Okay.
Homework, I know you're presenting it right now. However, I submitted sometimes not using this method. So do I resubmit it, or I don't know how to go about it?
Okay, it's actually kind of hard to hear you, but I think I'm all about resubmitting. Yes, I caught that part. Like if you already submitted homework, if you already got some points on it, but you didn't get all the points and you want your apps, in your case right now, everybody got some points who submitted it and they haven't gotten all because I haven't even looked at it in detail yet. And I'm assuming that most people haven't finished it yet. So, sorry. So you are, at any time, you are welcome to re-upload. Absolutely. Yes. Ideally, if you do more or you make corrections or you just improve in any way, ideally, you'll upload a new file and ideally you'll still leave the old file and just make it clear to me which file you want me to look at. Just number them or say this is the most recent one or whatever. But you can keep uploading, all of you can keep uploading improvements as much as you want, and you'll get points for that. But ideally it'd be great if you keep the old, just so I can see how hard you're working, just so I can see that you're actually revising and updating and improving, not just starting for the first time. But yes, you can re-upload. Does that make, and it's hard to hear you, but does that make sense?
Yeah, it does. Thank you.
Okay, great. Thank you. All right, well, but these are great questions, everybody. I mean, and especially great question. And by one final way to put this to everybody, even though this is the second physics course in life for most of you, and it's the second time with me for some of you, no matter what, we are in rough draft. I'm a big believer, like almost everything in life is a rough draft until it isn't. I mean, like maybe whatever's written on your tombstone is not a rough draft, and not to be gross, but like, I really believe like everything is just like, everything is progress, not perfection. So what I'm trying to say right now is there is not the only point in this class that anybody in this room right now cannot get is 1 point on the first game turn number 1, which technically was worth 5 points and technically had to be handed in by midnight that night to be gotten all the 5 points. But actually, I think every one of you has done it, I think. But with that, just that one, if anybody turns it in now, they'll get 4 points out of 5, which is no big deal at all. That's it. But with everything else, all the points, you're all still subject to getting all of them. Like nobody has done any irrevocable damage yet at all, believe me. And I will let you know once we're at a point where like some things are not attainable anymore, but it's going to be hard to get to that point. Everything is attainable for everybody still. It just to be clear on, like, no one's done irrevocable damage. And anyway, okay, but hopefully that's clear. All right, so I think Douglas's questions were answered. I think, let me know if they were not. You could put in the chat if I did, or you said that I did. Okay. All right, so, all right, I'm looking at the time, so it's 4:11, okay. So I've done step 1, the diagram and the fact pattern. Okay, so now I go to step 2. Step 2 is, what is the question? Literally, what is the question? And this is your distilled version, your best understanding summary of what the question is. It's not my exact words, it's not copying and pasting from the sheet, it's a distillation, and it could be symbolic. So I just wrote here, at x equals x naught, F equals question mark, like that's the question, right? I believe at the very first position of this phenomenon, what is the force? Compute the force that the spring is exerting on the mass. And here too is note, I don't need F net equals MA yet, and I don't need a whole free body diagram yet. I mean, again, I love Douglas's question, but I don't even need to know any of the other forces to be able to answer this. This is just asking literally what is, in other words, it's not asking the net force. It's just asking what is the force that the spring itself is exerting on the mass at this point. Note one other thing, please. One thing that I put in my diagram, that's one of the important aspects of a diagram, is labeling all the constants and variables that will be used throughout the math, and particularly labeling the coordinate directions. Like I've labeled that anything to the right of 0 is positive and anything to the left of 0 is negative. That is a choice. You might make a different choice, which is why, and that's fine. But that's actually why I have to make the choice clear. Since it's a choice, you don't know it until it's explicated. So I've explicitly stated that to the right from here on in will be known as positive, and to the left from here on in will be known as negative. So now I'm going to calculate the force at that positive position, x naught of 15 centimeters. So I turn the page and I go to step, so that was step 2, is what is the question? The question is, at x equals x naught, F equals question mark. Okay, now I go to step 3, GDP, general definitions and principles. So I write down something that is true even before I walked into this homework assignment, something that is just true that I'm going to use in the homework assignment. And that truth is Hooke's law for a well-behaved spring, F equals negative kx, where it's assumed in the whole, so this is like almost the definition of elasticity is F equals negative kx. This is what it means to be an elastic force. And F is a force measured in newtons. X is a displacement from equilibrium measured in meters. And K is stiffness constant, that which identifies the spring measured in newtons per meter. So this is just a plug and chug. I'm just walking you through so we can all be on the same procedural page here. So I'm just calculating the F that is exerted at that position X. So it's negative 200 newtons per meter. I believe 200 was the given. Stop me. Yeah, it was. Yeah. 200 newtons per meter times 0.15 meters. Okay. So the meters cancel out and you get negative 30 newtons. And then step 5, final answer circled. I circled that final answer and I'm done with the problem. Notice my final answer, besides being circled, my final answer is a complete thought, right? It is a statement. The original question is, what is F equal to? The final answer is F is equal to negative 30 units, in this case, newtons, right? It's a complete statement of science. So I'm done. I mean, I know that was all just question 1, but that's just a walkthrough of how we would do question 1. One little minor thing, classic question that I often get at this moment is, wait, okay, but I put F equals positive 30 newtons. Would you take off points or would that be wrong? Blah, 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 blah. Here's the deal. 30 newtons positive could be right if you designated the left direction as positive and you designated the right direction as negative. You could do that. And if you made that choice and you designated or explicated that choice, then your answer would have to be F equals positive 30 newtons. But the thing is, if you did make that choice, you can't just make it in your head. You'd have to make that choice clear. The thing about negative and positive signs is they remind us constantly to be conscious and explicit in our coordinate system setups. Coordinate systems become increasingly important and increasingly complicated as physics progresses. So the truth of the matter is, really, if you didn't put a negative sign at all because you just didn't even think about that at all, then you do want to think about it. And the key point of that negative, the negative means that the spring is pulling in the direction that's opposite to the displacement of the mass. If the mass is to the right of the equilibrium, then it is important to know that the spring is pulling to the left toward equilibrium. And if and when that mass ends up on the other side, then the spring will pull the other way. Okay, so I mean, so the answer is, yeah, it is negative 30 newtons, assuming that I labeled the right side positive. Okay, we have 3 minutes. 3 minutes. I'm going to go on and say this just because I know we will speed up. I promise you all of this will speed up. I promise. Otherwise, I'll bore myself. In a little effort to speed up, I'll just tell you this. I think the answers to the next 2 questions, just so you have satisfaction, if the next question was, what's the acceleration at that place, which I believe it was. I believe the next question is, what's the acceleration? Stop me from, actually, can I just get confirmation? We have 2 minutes. Was the next question, what's the acceleration at X equals negative? Great. Thank you, Amanda. Awesome. Thank you, Amanda. Then the answer is negative 100 meters per second squared. I mean, if this one's negative 30 newtons, then the next answer is negative 100 meters per second squared. If you left off the negative sign, it's not a crisis, but if this one's negative, then that one should be negative. And it's not a crisis. I get it if you forgot about the negative sign, but let's be clear. It is actually part of the answer, negative 100. And let me say also, and of course you can revise, that's why we're talking about this. You can fix something and re-upload, blah, blah, blah. But I'm going to go on to the next question. We'll stop with that one at 4:20. But I believe the answer to number 2 is A equals negative 100 meters per second squared. The negative sign does not mean slowing down. We all learned this last semester, but it is still a subtle and possibly confusing concept. There's no shame in rethinking about the fact that when I say that an acceleration is negative, that does not necessarily mean a slowdown. And in fact, in this case, it most definitely does not. The negative here means it's accelerating in the leftward direction. Right now, the velocity of this thing is 0. It's being held still. If we let it go, it's going to start moving to the left faster and faster to the left. And the left is the negative direction. So we would get a negative acceleration, which means speeding up in the negative, i.e. left direction, right? Speeding up, not slowing down. Finally, and stop me if that doesn't make sense, or stop me next time. Finally, for the question 3, which is where we'll end for today, question 3. It then asks, what's the acceleration at x equals 0? Not x sub 0, but x equals 0. At that point, F equals 0. If you plug back into Hooke's law, like we just did here, at the equilibrium position, the spring is not exerting a force anymore. That's why we call it equilibrium. So the force on the object is 0 then. The acceleration at equilibrium is 0 meters per second squared. Those are the first three answers. And let me put those in context before we end. Note that means the acceleration is changing along the way as this mass travels. It started with an acceleration of -100, and apparently that acceleration is changing continuously until it arrives at a value of 0. So this is not a constant acceleration situation. Just note to self. Okay, that is it for today. You guys have been very, very patient, very super, everybody's on top of things. I will wait until the last person goes if you have questions, but if not, please have a good one. And the homework has been extended till next Wednesday. So have a good day. Great. Thank you. Thank you, Caitlin. Thank you,
Bye,
Amanda.
Professor. Have a good day.
Awesome. You too. And I'll see you Monday, or I'll see you Wednesday. Awesome. Thank you, guys.
I do have a question,
Oh,
Professor.
yeah, absolutely. Let me turn off the recording. Hang on. But yes, awesome, Caroline. One sec.